a nice day. Can't wait to sit back and have a drink. The plan is simple. Okay, here we are on day 2. I have the main air chamber. Let's do the math. So this has a diameter of 3 inches. Radius of it would be 1.5 inches. So it's got let's say 5 feet, 424 cubic inches of air. I have a potato here. I have absolutely no clue if this is actually going to work, but we will see. It actually shot surprisingly well. Ready, fire. Oh shit. Okay, here I am on probably the final test for this. So I found a pipe that I can use as the new barrel. That's 3/4 of an inch, 3/4 of an inch, and then 3 inches. So I have this all a bit better set up. I've connected the solenoid to the power supply through a kind of Wago connector instead of wire nuts, and yeah, I'm gonna try and shove a cherry down here and see how far I can get it to shoot. So I'm just using like a tire iron to shove this in, which probably isn't very good way of doing this. Oh, this isn't sealing very well. But yowza. It has quite a lot of kickback now too. Okay, let's say that we want to calculate the distance that the object released from my cannon is going to travel. We can represent my cannon just as this, let's say, and then represent the object that it's releasing as a point. This point, after leaving the cannon, is going to be imparted with a velocity, which we'll call this. That velocity, if we're releasing it from an angle theta, and let's call theta in this case 45 degrees, is going to have a horizontal and a vertical component, right? So in the real world, we only see the velocity as it moving in a certain direction. But we can represent that direction with two different components, the horizontal and vertical. And if we're saying that theta is 45 degrees, then these two velocities are going to be equal. So what we can also do, given this information, is plot the distance above the ground and the final distance that this object is going to travel. So if we're trying to find the final distance, first we're going to have to find how long it's in the air. Because let's say that d is equal to vt times plus 1/2 at squared. So in this case, we don't initially know for the d, which is the x component of the velocity, the t, which is the time it's going to be in the air. But what we do know is each of their velocities. So what we can find is the t for this equation. So let's call this dx, and then we can represent a new graph, dy is equal to 1/2 at, or it doesn't need the 1/2, but vt plus 1/2 at squared. So that's dy. And I don't know the exact velocities in this situation, but if we're making a graph of time and then distance in the y direction from the ground, it's going to look like this, assuming that we're leaving the object from 0. In this case, I'm releasing the object from an incline, but it's not really going to make a huge difference. So from this graph, we can see that it's parabolic. It's leaving at 0 and finally hitting the ground at 0, and then it's reaching a point in the middle. This is because t is squared, and then the in the acceleration, but in the velocity it's not. So from this, we can get the time it's going to be in the air by finding 0, and then that is the t for our input for this equation. And given that, using the velocity of this projectile, we can find the distance it'll travel.